All right, I hear the recording in progress. So let's get back to where we were. Okay, so we're here. I was supposed to do 6.5, and I'm actually done with the chapter. So I was going to sneak in a little bit of 7.1, maybe even 7.2, but whatever I talk about in 7.1, 7.2 will not be on Friday's exam. Okay, so let's talk a little bit more about the exam. Some of this is repetition, but that's by design. Some of you have had me in the past, you know I repeat myself quite a bit. And the reason for the repetition is, well, not everybody hears it the first time, or some people were absent. And it really gives people no excuse, I would hope, that they say, oh, I didn't know this was the rule. And I ended up saying it, what, 2, 3, 4 times. All right, so first exam is Friday. By the way, reminder, Monday is a holiday for Labor Day, so no school on Monday. So I thought that was a nice, excuse me, thought it was a nice time to have the exam. Okay, coverage is here. This is what you're responsible for. Okay, so you turned in this homework. I'll take it anytime after class Thursday. Okay, but the latest I'll take it is half an hour after the exam ends. Okay, so let's talk a little bit more about that. Okay, so coverage again is this. You have to turn this into homework. I have a 70% homework rule. You must submit at least 70% of the homework in order for me to grade it. Again, that 70% is really not that hard considering I do a great percentage. Sometimes I end up doing 70% of the homework anyway, in which case all you got to do is copy it and submit to me. By the way, not all the homework might fit on one email or one file. You might have to break it up into 2. Sometimes some students would break it into 6.1 to 6.3 and then 6.3 to 6.5. Some students just do one section for each file, like one file for 6.1, another for 6.2, another for 6, however you want to do it is perfectly fine. All right. I give about 10 questions. So the questions are very similar to the homework. I don't give any tricks. I don't give any surprises. So the most likely scenarios for 5 sections, I would give you 2 questions per section. Okay, you have the entire time, 50 minutes from 8:10 to 9 o'clock. And this is the one time, again, for the exams that you must show up. I will be taking attendance. So I know attendance is optional all the other days, but for this one, you have to show up, have your actual camera on, true background, no Golden Gate Bridge, no outer space or anything like that. Have your first and last name as on my roll sheet. Don't make me guess what your name is. And keep yourself muted. If you have any questions during the exam, put it in the chat. Okay, so you have 8:10 to 9 o'clock. At 9 o'clock, I'll close the Zoom session as normal. Then you have 5 minutes to click, 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 take pictures on your cell phone. And do the same thing for the homework. So now that you've already had a couple of quizzes, you know what to do. You submit everything the same way, just like the quizzes. Submit the homework the same way, the exams the same way. Just take a picture on your cell phone or scan. I would actually prefer scanning because scanning, like on Cam Scanner, that quality comes out much better than just a regular, cell phone picture. But anyway, that's fine. Let's see what else. You can have one cheat sheet, one formula sheet, front and back, 8.5 by 11. Put anything you want, formulas, sample problems, and that'll be fine. Right? Okay, and let's see. If you finish early, you can leave early, of course. 9 o'clock, I'll close the Zoom session. You have until 9:05 to submit the tests, and you have until 9:30 a.m. to submit the homework. But if you want to submit the homework early, you may, then you don't have to worry about it anymore. And that is it with that. Let's see, what else? Formula sheet, talked about that. Show all your work. You do the problems just like we did in class. You can look at the videos. Okay, so when in doubt, show more work rather than less work. Okay, so I don't accept it if you just give me an answer and no work. I need to see your work. And besides, that way I can give partial credit. And let's see what else. Yeah, you have to show me your ID. So if you haven't already done so, do something like this, right? For a class like this, obviously I don't get to know what you look like. So how do I know that's really you taking the test? So just show me your ID, school ID or driver license. Just cover everything else, except I just need your picture and your name. Cover up, your date of birth, your height, weight, address, all that information that you may not want to share with me. So if you don't do that, I'm not going to count your test. So you have to submit that to me also. All right. And let's see, if I have time, I'll probably say the same thing tomorrow, but this is just, again, for repetition purposes. So any questions about that? Homework and exam on Friday and so forth. I'll send the exam on Canvas announcements. So maybe like 8:01, 8:02 a.m. I'll send through Canvas announcements. And then once you get it, just join immediately and you can just work until 9 o'clock. Okay, so any questions about that, please? All right, so I already had some requests for review questions, so let me go back and do some. So this is just my own review, and some of you had questions about these anyway. 6.339, you have the graph of y squared minus x squared equals 1, and y equals 2, bounded by y squared minus x squared equals 1 and y equals 2, and you're spinning it about the x-axis. Okay, this is a hyperbola. Looks like that and like that. We'll do more with hyperbolas later. So there's a branch that goes up and down. If the x squared were positive and the y squared were negative, it would go left and right. This one goes up and down. And y equals 2, we know is a horizontal line. So this must be the region. And we're spinning about the x-axis. Okay. Right, so it looks like it's easy to do this method, or actually the washer method. Okay, washer method is really the disk method twice. You have a bigger disk and a smaller disk. So I'll slice delta x. Okay, how do I find out where they touch? I would set them equal to each other. I've got a little bit of algebra here. Solve for y, that's easy. Add x squared and take the square root. I trust you can do that algebra, right? Add x squared, square root. So this is y equals square root of 1 plus x squared. This is y equals 2. All right, where do they touch? Well, set them equal. So plug in 2, it gives me 4. Put a 2 here, right? So 2 squared minus x squared equals 1. That gives me x squared is 3, so x is plus or minus radical 3. So the graph goes from negative radical 3 to radical 3, and because of symmetry, I'll integrate from 0 to radical 3 and double my answer. So the volume is 2 integral from 0 to radical 3. Yes, I could go from negative radical 3 to radical 3, but I'm going to go from 0 to radical 3 because of the symmetry. Now you have to make sure you have that symmetry. Okay, so if you did not have a symmetric graph, don't just automatically say, oh, if I go from negative b to positive b, I automatically just go from 0 to b and double it. No, you must have that symmetry. So let's say the graph went something like that, right? Then no, you would not be able to do that symmetry. So I'll double from 2 to radical 3. Okay, so I have a big R and a little r. My bigger radius is just 2. My smaller radius is radical 1 plus x squared. So pi big R squared minus pi little r squared dx. Factor out the pi. 4 minus radical 1 plus x squared squared is just 1 plus x squared. It's very nice. So that's 4 minus 1 minus x squared, 3 minus x squared. All right, so 2 pi, integral of 3 is 3x. Integral of negative x squared is x cubed over 3. Remember, you can always double check by differentiation. The derivative of this should be that from 0 to radical 3. Plug in 0, you get 0. Plug in radical 3, 3 radical 3. This one is 3 radical 3 in the numerator because it's radical 3 times radical 3 times radical 3. Well, 2 of them give me a 3. So it's 3 radical 3 over 3. 3's cancel out. So 2 pi times 2 radical 3. Final answer is 4 pi radical 3. Okay. All right, so that's that one. A quick rehash of 13A. Somebody asked for 13A, although I think we already did it. 6.4, 13A was the rope problem. Okay, so it was hanging over the side of a building, right? 50 feet long, 0.5 pounds per foot. How much work is done in pulling the rope to the top of the building? So x equals 0, x equals 50. There's a delta x. If I have a very tiny slice, the rope pieces are all moving the same distance, which is x. So delta W, change in work, is the density 0.5 pounds per foot times delta x feet. Feet cancel out, so now I have pounds. It's a force times the distance. The distance is x. So 0.5x delta x foot-pounds. So that's why I integrate. In the integral, delta x changes to dx. So integral from 0 to 50 of 0.5x dx. I just said, etc. You can do that. Came out to be 625 foot-pounds. And then 6.5. Just for practice, I'm going to show you a problem. I'll call it 3-star because it's not really number 3. This was number 3 in a previous edition, but it's good practice anyway. So this is not a problem in the text. I make up my own, let's say. So g of x equals cube root of x from 1 to 8. What's the average value of the function? So the average value is simply integral divided by the length. Right? So what's the length of the interval from 1 to 8? Well, 8 minus 1 is 7. So I divide by 7, but normally we say multiply by 1/7 because it looks too weird to, take an integral and divide by 7. Integral divided by 7, that just looks too weird. So we take 1/7 and then multiply by the integral. Cube root of x means x to the 1/3. All right, so 1/7. X to the 4/3 divided by 4/3 means times 3/4 from 1 to 8. And this arithmetic comes out to be 3 over 28. Okay, plug in 8 to the 4/3. Plug in 1 to the 4/3. Well, 1 raised to anything is 1. 8 to the 4/3 means cube root of 8. Cube root of 8 is 2. And then 2 to the 4th is 16. And 16 minus 1 is 15. So 3 over 28 times 15, 45 over 28. Okay, and then number 7 is in our homework. Find the average value of cosine to the 4th x sine x from 0 to pi. So I go 1 over pi minus 0, 1 over pi, times the integral from 0 to pi, cosine to the 4th sine x dx. I'm going to do a u substitution. Now, derivative of cosine is almost sine, negative sine. Derivative of sine is cosine, but you don't want to go that way because I don't really have cosine, I have cosine to the 4th. So that tells me let u be cosine of x. Du is negative sine x dx. Derivative of cosine is negative sine. I need a negative, that's okay, just put a -1 inside and a -1 outside. Which means outside I now have -1 over pi. And I change the limits of integration. I plug in 0, cosine of 0 is 1. Plug in pi, cosine of pi is -1. So I have -1 to pi integral from 1 to -1. That's backwards, but that's actually okay. I'm going to apply the negative on these and I'll switch these two. So cosine to the 4th now becomes u to the 4th. -1 sine x dx, -1 sine x dx is my du. So again, turn this around and you get the best of both worlds. Not only do I get to lose a negative, but I get the smaller number on the bottom and the bigger number on top, right? Remember from the end of Calc 1, the integral from a to b is the opposite of the integral from b to a. So I switch these two and change the sign. That makes this positive, and the smaller numbers here, the bigger numbers here, and that's the way I want it. And you could integrate from here, but I'll use symmetry. U to the 4th, that's like x to the 4th. We know it looks something like that. I'm going to get a symmetry. Yes, it's an even function. So again, if I'm integrating from -1 to 1, I might as well just integrate from 0 to 1 and double it. Makes the calculation much nicer, right? Think of the graph of u to the fourth. That's like saying, what's the graph of x to the fourth? Something like that, right? So if I go from -1 to +1, the graph is symmetric. So I can take advantage of it. Again, you must see the symmetry, right? So if you have a graph, let's say that goes like that, from -1 to 1, don't do 0 to 1, because you don't have the same area between -1 and 0 as you do for 0 to 1. Because of the symmetry here, you can take advantage of that. Right? So if I'm going to integrate, let's say from -1 to 1, I get just as much area here as over here. But don't do that for a situation like this. All right, so I multiply by 2 and just integrate from 0 to 1. That's 2 over pi. U to the 5th over 5, from 0 to 1, that's 2 over 5 pi. Plug in 1, 1 to the 5th power is 1, minus 0 to the 5th power is 0. So final answer is 2 over 5 pi. Right, so that's a little bit of a review right there. Okay, and now I'm going to get started with some of chapter 7, 7.1. I alluded to a little bit of integration by parts. And so anything I say now on integration by parts is extra. It will not be on this test. Oops, that's not our class. So for coverage for the test on Friday, just this, I'm sneaking in some of 7.1, which I was originally not going to start until Tuesday. Remember, Monday's a holiday. So as I lecture on this, kind of look at it half-heartedly until after the test. So I would say don't even look at it until after you take the test, right? But I'm just going to go ahead. You always can look at the video a little bit later. All right, so 7.1, something called integration by parts. Page 472, the formula you want to use and put on your next cheat sheet, not on Friday's cheat sheet, but the next one. Integral of u dv equals uv minus the integral of v du. Yes, you probably don't even know what that means now, unless you've seen this before, but go ahead and put it down. So what about this one? It's equivalent. These are the same. I like this one better because it's shorter, right? So technically you could use this one, but I like this version better. So what is it? How do you use it? And so forth. Okay. So the first thing is to show you why it works, not just give it to you. So a little bit of an explanation as to why it works. Integration by parts, it's actually the integral form of the product rule. All right, so recall from the product rule, the derivative of u times v, where u and v are functions of x, dx, is u dv dx plus v du dx using the Leibniz notation, L-E-I-B-N-I-Z. Leibniz notation, which you may have heard from the Calc 1 teacher, means the d stuff, like dy dx or d squared y over dx squared. That's the so-called Leibniz notation. Leibniz is one of the co-founders of calculus, along with Sir Isaac Newton. They're the co-founders of calculus. So this is the product rule, right? First times the derivative of the second, plus second times the derivative of the first. So the derivative of u times v with respect to x is u dv dx plus v du dx. Or using differential notation, remember you had a section on differentials in Calc 1, d of uv is equal to u dv plus v du. Another way you can think of it is if you pretend you multiply both sides by dx, right? As if dx was a variable. Multiply both sides by dx, all the dx's are gone. We just have that. And notice that is just this. It's like just looking at the numerators. Right? If you ignore the denominators, it looks like this. Right, then I'm going to integrate both sides. So integral of d of uv is the integral of u dv plus v du. Integral of a derivative. If you have the integral of a derivative, you know the derivative and integral are opposite operations. They just cancel each other out. So you just have uv, right? If you differentiate and then you immediately integrate, well, you're back to where you started from, right? That's just like saying, you know, I'm going to add 5 and I'll quickly subtract 5. I'll take the cube root and then a cube, then you're back to where you started from. So that's just uv. This thing, I decided to split into two. We have a property of integrals that the integral of a sum is the sum of the integrals. That means I can write it as the integral of u dv plus the integral of v du. And then I subtract the integral of v du on both sides, subtract on both sides. And I have the formula, except I'm going to put the right-hand side on the left and the left on the right. In other words, if you have a equals b, that's the same thing as saying b equals a. So if I subtract this on both sides and decide to put this on the left and this on the right, this is what you end up with. Integral of u dv equals uv minus integral of v du. Okay, so that's the formula in case, you know, you may not have understood all this, but that's okay. I'm supposed to know this. And you just say, oh yeah, my teacher showed me where it came from. Rather than just saying, here, it is, use it. You saw a derivation as to where it came from. So here's the formula for integration by parts. It says memorize here. You don't have to memorize it. The last time I taught, we were face-to-face, and I made my class memorize it. But since you can have a cheat sheet, you don't have to memorize it. So definitely put this on your next cheat sheet. Again, not on the cheat sheet for Friday's test, but for the next test, whenever that is. So that would be for what, Friday, 9/24. So 3 weeks away, or 3.5 weeks away, or whatever, for test number 2. All right, so that's the formula that you want to use. How does it work? Why do I do it? Okay. What's happening in general is you have a more difficult integral. You change it to this, and hopefully by doing this, and I say hopefully because there's no guarantee it works if you do it the incorrect way, but we hope that this integral is nicer than this one. Okay, so again, by doing this change, integral of u dv, and I do all this stuff, this integral hopefully comes out to be better than this. Okay, I notice there's 4 parts to this expression. There's a u, a v, a du, and dv. So there's 4 parts. That's why it's called integration by parts. So every problem for this, there's a u, a v, a du, and a dv. Once you figure out what's the u, v, du, and dv, then you just throw it into the formula. You might be saying right now, I don't get it. And by the way, yeah, I don't expect you to study any of this until after the test on Friday. Okay. And yeah, even then you may not want to do it. I know it's a weekend, it's a 3-day weekend, Labor Day. So I don't blame you if you don't want to look at it until we get back from Labor Day. But that's okay. So 7.1 star, and again, 1 star because this is not our real number 1. This was number 1 in the 7th edition, not the 8th edition, but that's okay. X squared ln x dx. All right, so from the original integral, I need to establish a u and a dv. Okay, so here's the original integral, x squared ln x dx. So something has to have a u, something has a dv. Okay, I choose to let u be ln x. You say, why don't you let u be x squared? We could, and I'll show you what happens in that instance. But let's say u is natural log of x, and dv is the rest of the stuff. dv is x squared dx. Okay, so if I call this u, ln x, and dv is the rest, x squared dx, and they don't have to be quote unquote next to each other. We know multiplication is commutative. You can change the order any way you want. So what I want you to realize is if I call this u and the rest of the stuff is dv, then I have an integral that looks like u dv. it does fit the mold, as it were. So u equals ln x, dv is x squared dx. Okay, the dv has to have the dx. So in other words, d, no d, no d. Okay, there's no d here, there's no d here, the d here, and a d here. Right, so there's my u, there's my dv, so it fits this. Now, this side you differentiate, this side you integrate. And I got too lazy to write the whole thing down. So differentiate, diff, I think you get that. Otherwise, I'd have to write differentiate, and here I'd have to write integrate. But within the context, I think if I write this, you know I mean differentiate, you know I mean integrate. Okay, what's the derivative of ln x? 1 over x. So I'm going to write du equals 1 over x dx. Again, using the Leibniz notation or differential notation, you just write du here equals the derivative dx. We did a section on differentials in Calc 1. Just put a du here, dx here, and then 1 over x. Alternatively, if you think back, if you don't like that, where does it come from? We wrote du dx in Calc 1, didn't we? Pretend I write du divided by dx, du dx. That's the Leibniz notation for the derivative. Du dx equals 1 over x. And then you multiply both sides by dx, and it looks like that. You differentiate this side. Integrate this side. So what's the integral of x squared? X cubed over 3. And right now, you don't have to put the plus c. Okay, so I'll go through that whole process again. Establish something to be a u and a dv. The u must not have the d, so ln x. And then the dv must go with the dx, so x squared dx. Yes, you might be saying, how do you know this isn't the u and this is the dv? That very well could be the case, and I'll show you a little bit. Later, okay, if I have time, why we prefer not to do that. Okay, so now I have 4 pieces, u, dv, du. See, how do I go from u to du? Differentiate. How do I go from dv to v? Integrate, the exact opposite. Okay, the formula, there's a u, a v, a du, and a dv. So I can just plug everything in. I have 4 parts. That's why it's called integration by parts. Right. So capital I, and this is my abbreviation for the original integral. If I want to talk about the original integral, I call it capital I. Okay, I'll just go ahead and say that's not standard. Not every instructor does that. This is just my own hang up, but I think it's a good hang up. Okay, I mean, the alternative is you have to write this all over again. So would you rather write integral x squared ln x dx again, or just write capital I? And for my course, the understanding will always be anytime I write capital I, it's the original integral. All right, the formula goes uv minus the integral of v du. So u times v is this. So 1/3 x cubed ln x minus the integral of v du. So v is this thing, 1/3 x cubed. Du was 1 over x dx. So here's the v du. Okay, so leave this one alone. And here, I don't really care how complicated the problem gets. I just leave it alone. I'm not doing anything with this. I'm not integrating it. I'm not differentiating it. Just write it. Minus, okay, clean that up. 1/3 comes outside. X cubed times 1 over x becomes x squared. Okay. And I know how to integrate this. So that's the whole idea behind integration by parts. You start off with an integral that maybe you don't recognize. Quite often it's a product, like this, x squared ln x. I transform it into blah, 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 minus a new integral. And the new integral turns out easier than my original. The original had x squared ln x. My new one just has an x squared, and I know how to integrate x squared. Okay, so just copy this stuff here. 1/3 x cubed over 3 plus c. Clean that up. So final answer is 1/3 x cubed ln x minus 1/9 x cubed plus c. And that's my final answer. Yes, I know that was a lot of stuff. All right, now, I've got this statement over here. We would usually choose to differentiate ln x rather than integrate ln x. And what do I mean by that? Okay. From Calc 1, what was the derivative of ln x? 1/x. Now, in Calc 1, do you remember what's the integral of ln x? Not the derivative. We know the derivative is 1/x. What's the antiderivative? In other words, what function is there whose derivative ends up being ln x? You may not remember that from Calc 1. There's a very good reason for that. It's not supposed to be covered in Calc 1. Okay. So your Calc 1 teacher may have shown it to you, may not have shown it to you, but it wasn't required. Okay. We will actually go over the integral of ln x. In fact, the way to prove the integral of ln x is also do integration of parts. Okay. We would normally choose to differentiate natural log of x rather than integrate ln x. Okay, so let me go back and address the issue of way back at the beginning. Suppose we said u equals x squared and dv was the rest of the stuff. That actually fits the mode. That fits this. Let this be u, let this be dv. That means I would be, what, differentiating this. That's easy. But I have to integrate this, right? So remember, this side you differentiate, this side I integrate. I would have to integrate ln x. We don't know what it is yet. Right? So for integration by parts, we would normally choose to differentiate ln x rather than integrate ln x. So if I have this integration by parts stuff and I see ln x, I definitely want to differentiate 1/x. I don't want to integrate. Now, if I have a polynomial, I don't mind. Like x squared, that doesn't bother me. X squared is easy to differentiate, 2x. X squared is easy to integrate, x cubed over 3. So if I have a polynomial, that never bothers me, right? Polynomials are easy to differentiate. They're also easy to integrate. So that doesn't bother me one way or the other. All right. Now let me show you problem 3. This one is actually on the homework. Integral of x cosine 5x dx. So one thing you may notice right away is one of the reasons why we will want to use integration by parts is they have a product. You're integrating a product, something times something. Now, you might say, why don't I just use the product rule? And there's a very good reason for that. There's no such thing as a product rule for integrals. There's no such thing as a quotient rule for integrals. Okay? Now, in Calc 1, there's a product rule for derivatives. You can always do the same thing, right? You have f times g, right? F times g, I know what to do. First times the derivative of the second, plus the second times the derivative of the first. That always works. Or a quotient rule, right? F over g is bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the square of the denominator, right? You can always do that. There is no product rule. There is no quotient rule for integrals. Your Calc 1 teacher may have told you that. Those of you that had me in Calc 1, you know I said that there is no such thing as a product rule. There's no such thing as a quotient rule. So, and in Calc 1, I said a major portion of Calc 2 is integrating a product or a quotient. Something times something, something divided by something. And you want to just say, oh, just do the product rule or quotient rule, but there's no such thing. So we had to do other tricks. And so that's where we are now. How do I do a product? So one trick is to do this thing called integration by parts. Okay. So let's do this integration by parts, which is right here. So I'm going to call that u. I'm going to call that dv. Let u be x, and dv is the rest. So the dv has to go with the dx. The u has to go with the x. So let u be x, dv is the rest of the stuff. So now this looks like the integral of u dv. And then once I get my parts, I do this. Now, there's another option. You could also say, how about I let u be cosine 5x and dv be x dx? That would also be a possibility. I'll show you what happens in that instance for this particular case. Okay. So here we go. U equals x, dv equals cosine 5x dx. Okay, differentiate this side, integrate this side. So derivative, integrate. So u equals x, du equals 1 dx. If it's 1 dx, you can just put dx, right? Second, a very easy way to think of this is you just d both sides. Just put a d here and a d here. U equals x, put a d there, du equals dx. Even though that says the same thing as du equals 1 dx because the derivative of x is 1. Or again, using the Leibniz notation, you would have written in Calc 1, du dx is equal to 1, and then multiply both sides by dx, and it looks like this. And this side, you integrate, right? So it's as if you put an integral here. So integral of cosine 5x. Okay, do you remember what's the integral of cosine? Sine, right? So sine of 5x, and now the chain rule in reverse. We talked about that the other day also. Okay. If I were to differentiate by the chain rule, I'd multiply by 5. Since I'm integrating, multiply by 1/5. Right? Again, you can only do that trick for constants. 1/5 sine 5x. Okay. Again, double check. What's the derivative of 1/5 sine 5x? You would go 1/5 cosine 5x times 5 by the chain rule. That 5 knocks out the 1/5, and there you go. So remember, differentiation and integration are opposite operations. So I say to myself, okay, if I differentiate by the chain rule at this step, I multiply by 5. Therefore, when I integrate, I divide by 5, I multiply by 1/5. Okay, so I have my u, v, du, dv, plug it into this guy. All right, so by formula u times v, u times v. So 1/5 times x times sine 5x, that times that. Normally you put the coefficient first, and then polynomial and then trig function. So u times v minus the integral of v du. So here's the v, du is the same as dx. So 1/5 sine 5x dx. Okay, and let's see, did I make the integral easier, right? I started off with x times a trig function. Now I just have a trig function. Okay, so it got better. By doing all this mess here, the original function, which had a product, something times something, polynomial times trig, now I just have a trig function. Right, so I leave alone the negative 1/5, then I integrate sine of 5x. Integral of sine is negative cosine, so negative cosine 5x, and then by the same reasoning, times 1/5. Okay, this negative 1/5, okay, that negative 1/5 is that. And now the integral of sine of 5x is negative cosine 5x times 1/5. By the same logic as over here. So I finally cleaned that up. That becomes a plus 1/25. So final answer, 1/5 x sine 5x plus 1/25 cosine 5x plus c. Final answer. Now, it might take a little while to do this, but if you were to go ahead and differentiate all this mess, if you do it the right way, it should end like that. Maybe I leave that to you as an exercise if you want to verify that sometime. Although again, I would say don't bother to try that until after the test on Friday. Okay, the problem's finished, but I'll dig a little bit deeper and then I'll be done actually. Okay, we speculated, suppose I let this be the u and these two combine to be the dv. In other words, let u be the cosine 5x and dv is x dx. So u is this, dv is the rest. That would qualify as the integral of u dv. That works. So let's see what happens there. U equals cosine 5x, du sorry, dv is x dx. Right, so differentiate this side, integrate this side. So differentiate. Derivative of cosine is negative sine. So negative sine 5x, then by the chain root times 5. So negative 5 sine 5x dx. Integrate. Integral of x is x squared over 2. U, v, du, dv. So uv is that times that, 1/2 x squared cosine 5x, minus the integral of v du. So v, let's see, that times that gives me negative 5/2 x squared sine of 5x dx. And take out the negative 5/2, double negative. So 1/2 x squared cosine 5x plus 5/2 integral of x squared sine 5x dx. Which is still true. This is still a true statement. But let's see what happened by doing this stuff. What did I start off with? I start off with x times a trig function. I got x squared times a trig function. So it got worse. The problem became worse. I went from x times a trig function to x squared times a trig function. So that tells me this is not the way to go. Okay. Now, by doing this one, let's see, I had x times a trig function. And then when I did all this stuff, I ended up with a trig function. Great. Here, I went from x times trig function to x squared times trig function. It got worse. All right, so that leads me to believe the following. And you can put this on your next cheat sheet. If you have to integrate a polynomial times a trig function or an exponential, normally let u be the polynomial and dv is the rest. Okay, so not the other way around from what we said. And then we said, if we have ln x times anything, ln x with whatever, let u be the ln x and dv is the rest. Why? Because I want to differentiate ln x. I don't want to integrate ln x. I'd rather differentiate ln x. Okay. All right, so at this stage, about 5 minutes left, a little bit more than 5 minutes. I was going to stop. Okay, again, anything I do in 7.1 is not going to be on the test. So we'll pick up, I'm a little bit ahead. We'll pick up with this stuff on Tuesday. And tomorrow, I was going to let you ask questions from chapter 6 for the entire time. Obviously, if you're not joining the class from 8 to 9, then of course you can't ask any questions, but you don't have to either. So I'm going to let you ask questions the entire time tomorrow, but if you don't have any, I'll just keep sneaking ahead with chapter 7 in case I fall behind. Because I recall exactly this time last year, right around Labor Day holiday, my internet went down for a whole week. So I lost a whole week's worth of material. So I'm guarding against that possibility by trying to sneak ahead if I can. All right. So you know what's happening tomorrow. You can ask questions, but if not, I'll just keep going with what I had. And the first test is Friday. And then we have a nice 3-day weekend after that. Okay, so let me stop the share and see the chat. If there's anything in the chat, and if not, we are finished for the day. Okay, so any questions, please? All right, I see nothing or hear nothing, so we'll call it a day. All right, have a good day, everybody. We'll see you next time. Okay, bye.
Thank you, Professor. Thanks.
Thank you. Bye.